All right, welcome everybody. I'm sure everybody must be tired. It's the end of the day, but I'm grateful that you guys showed up. So, thank you for coming to my talk. I'm going to be talking about ASN one parsers, namely in the Intel baseband. A little about me, some self-promotion. I work for Vigilant Labs. It's a security research company, and I'm a security researcher there. Um, My motivation for giving this talk was just to share some research that I've done on this topic because I'm probably, I don't know, just before I forget it forever, because I don't think I'm going to be working on this in the near future. So, yeah, it was just a way to share with you guys. And originally, I thought this talk wouldn't be relevant because, I wanted to use it as an excuse to visit Korea for ZeroCon, but unfortunately I couldn't go there, so I decided to give the talk here. So we're we're gonna see how it's gonna go. So just some prior work. There's been some prior work on the Intel baseband, and it was from Nico Gold, Secures, and there's another talk from a guy. I mean, I think his name is actually Guy. So yeah. Let's talk about the Intel Infineon baseband. The reason why I decided to look at this target was for Pwn to Own 2018, so that's already like 5 years ago. It seemed like an interesting challenge, and at the time it seemed impactful because it was used on the latest iPhone. Um, what is Intel Infineon? It's from this company called Infineon AG, and it's a German semiconductor company, and they had like a wireless solutions business that was acquired by Intel in 2011, and it became Intel Mobile Communications. And in 2019, actually, um, a year after I did research on this, it was acquired by Apple because it was kind of a bumpy road for the Intel modem because they couldn't really compete with essentially any of the other vendors. They had like performance issues, like iPhones that were using this baseband were slower. Their battery would run out faster and stuff like that. So they also tried to make 5G work. It never worked out. So they decided to just give up, and Apple purchased them in 2019. So I guess we can call it the Apple Infineon now. So it's called like Intel XMM modem, at least that's the way I know it. And it's just the embedded software that's running on the baseband processor, which is the processor that handles cellular, 2G, 3G, LTE. And it's used in several devices today. I guess, you can find it in older iPhone models, Tesla cars today, and, some PCs in dongles and stuff like that. Um, so the baseband firmware for the Intel Infineon can be found in the IPSW images. When you unpack them, you'll find it in firmware slash sys underscore SW elf. And yes, it is an elf that you can just load in IDA, which is something that's pretty rare when you're doing research on firmware like this. It doesn't have any symbols, but it does have some debug strings, so we're going to try to work with that. And basically, the fact is you can't avoid reversing it because you're not going to find like leaked source code or stuff like that. So you just have to reverse it. This talk is centered around the ARM version, but I just want to note that there's x86 versions. So when iPhone 11 came out, it turns out I tried to load the firmware like I used to, but it was looking like garbage in IDA, and it turns out it was actually x86. So yeah, it seems like they just did it for that one version. So I don't know. Could have been like, I don't know, a licensing thing. I don't know. I'm not gonna speculate on that. It's a real-time operating system, and it's very typical in time-sensitive applications. So I think at least all the basebands I've ever looked at are running some kind of RTOS. And the way like a RTOS works, you have the power on or the reset, and then go to the bootloader, and the bootloader will do some stuff, load the RTOS kernel, which will set up memory, initialize the tasks, and tasks tasks here, it's basically just functions essentially that are running, or threads, let's just call them threads, and then it sets up like a scheduler that will, divide the resources between these threads. So this is like some pseudocode. It's really, really simplified. I didn't want to blast you guys with too much code, but this is essentially what they look like in this modem. It like task entry, it will allocate some like context structure, initialize the task, and then it'll enter a while loop that will just receive messages from a queue, process them in some kind of way. And this is like how the different tasks communicate with each other. They'll put stuff on a task queue and retrieve messages from their queue that other tasks have posted for them. So, like I was saying, it does have debug strings, and this is something very useful for us. And these are some strings that were pretty interesting that I found in there. Like you have UTA OS, thread create, thread create, thread start, whatever. This is clearly like some functions that are most likely used to create threads. That was my guess at the time anyway. And luckily the guess was correct, but this is how the initializing function looks like. It will like, this is also, kind of pseudocode, but it just goes through like some array where all the tasks are described, and it will like create their message queue, create the thread, and then start the thread. So what does the table that I'm talking about look like? It's something like this, and it'll have a string for the name of the task / thread, and then the entry point for it, and then you'll have like a queue ID or like signaling ID. Yeah, that's basically the basics for reversing this thing, I guess. So now let's talk about bug hunting and attack surface selection. I was hesitant when I was picking the name for this talk because I wanted to convey the idea that it's more about selecting attack surfaces than really ASN1, and you'll see what I mean by that. So my original plan when looking at this target was to, read through the code, identify cellular stack, because the RTOS has a bunch of other stuff going on, but we're only interested in the cellular stack. So I wanted to look for that, and then audit the different layers, different messages, find bugs, like a simple, easy plan. But unfortunately, there's some things that didn't go as planned. We'll see. Initial reverse engineering identified the different tasks, just reading from the entry point, stuff like that. And looking at the task names and debug strings, I tried to guess the functionality of these tasks, and then I tried to confirm or deny the validity of these guesses. So this is the array I showed you earlier. And as we can see, when I see stuff like, I've done this a long time. So when I see stuff like RLC, RRC, or MM/GMM, I can try to guess that it stands for radio link control or, mobility management, which are some of the protocols of the GSM stack. But like I was saying, when we look at some of those entry functions, this is just a video I took for you guys to show you what it kind of looks like in IDA. Basically you get the point. So it's just very, very huge functions. Might be like some compiler inlining. At first, I thought it was generated functions, but that didn't really make sense. So I think it's probably like some inlining or something going on, but it takes minutes to decompile these functions in IDA, and if you try to change the function prototype and then hit F5, you wait minutes again, so it wasn't really easy to work with this. So the original plan was not gonna cut it, so like I said, you can't avoid reverse engineering it because you don't have source, but we can try to find a way to guide it. And that's what I meant by attack surface selection. So instead of reading the code, let's just try to read like the GSM specs and identify complex features in there. And then, then we know what we're trying to find during reverse engineering instead of just looking at everything and trying to see if we find a buggy portion. So the GSM specs, we have different technical standards. This is just a list, but basically there's one for the core layer 3 of GSM. There's some that describe, for example, SMS, how they work, and there's another one that has this thing called supplementary services. So yeah, supplementary services piqued my interest, mainly because it was something that I had never looked at before. But basically what they are is just additional features in the spec that allow to enhance user experience. Telcos can customize their networks using supplementary services, and it just allows them to do things more than just receiving calls and sending texts. It has things like call forwarding, call holding, call waiting, stuff like that. And USSD, I know some of you might be familiar with that. And also has this thing called location services. And it uses ASN1 to encode data. And when I saw that, I was like, that's pretty interesting, because I know there's been prior success stories from people looking at ASN1 decoders. So that's when I was like, oh, maybe there might be something here. So for those that don't know, a little primer on ASN1. It stands for Abstract Syntax Notation 1. It's just a notation that describes data structures. And it's developed by this thing called ITU. And it's used in a bunch of, it's used in telecommunications, but as some of you might know, it's also used like in parsing certificates, stuff like that. So, and it's just a data representation. So the key is that it defines the data and independent of its encoding. So it doesn't really describe what it should look like physically, but it does describe just the structure of the data. And it has various data types. There's primitive types, like you all know, the standard ones, integers, strings. It also has constructed types like sequences and sets. And the way it's designed is such that you can add existing fields to new data structures, when you update and stuff without breaking compatibility. And it's using these things that are called encoding rules, which is basically how do you convert the data structures to a physical representation. Those are the encoding rules. So just an example of what ASN1 looks like. I mean, this is just a simple random ASN1 definition. So just the person data structure, it's a sequence. And it contains various fields. As you can see, there's like integers, octet strings, which is just a string of bytes. And as you can see, some of them are constructed, like the address field. The address field is a constructed field with strings inside, etc. So as you can see, it can be as complex as you want it to be. So the things in brackets are called tags, and they just allow you to uniquely identify strings inside the ASN1 message, I guess. So we have this thing called basic encoding rules. It's like the most widely used encoding rules, and it's pretty much just like TLV, which is type length value. And these are examples of how they are encoded, and it has subsets that are called DER and CAR. I mean, it doesn't really matter, but we also have the packed encoding rules, which is designed for efficiency, and minimal overhead. Yeah, so I think it's interesting as an attack surface because you can have potential issues in ASN1 decoders. Obviously, the way data is decoded, there's just too many corner cases that developers need to consider. We also have potential issues in handling of the decoded data because they're building data structures from this ASN stuff they're parsing, and you can end up having very complex data structures that you need to recover from this. So the first thing I needed to do was to identify the supplementary services task, and I mean, just with some elbow grease, I was able to find that it's called MNS, and just reversing with some cross-referencing of the specifications, looking for constants, stuff like that, and it turns out it's also another large, messy function. But luckily, I guess, it's not as large as the other one. But yeah, so this time, we're lucky because it's only 2,300 lines. And yeah, just like I said before, there's no way we can avoid reversing it. So this is, I didn't want you to look at that ugly thing, so I kind of made it simpler for you. This is kind of how it works. A very simplified version, but essentially it like processes the data, allocates something like a signal that it needs to send to another task for further processing. Yeah. So let's talk about vulnerability analysis. I'll tell you about my findings in this. One of the components of supplementary services is called location services, and it's just a set of features that allows to locate, I guess, devices. You have, it's used in emergency services where you need to locate a caller, tracking like an asset, because vehicles can also have, can also be running some kind of GSM stack. And yeah, navigation, location-based advertising. And I mean, since we're all hackers, I'm thinking some of you are looking at this with like a different eye. And yeah, of course, while it can be used for like legitimate purposes, there's nothing preventing a bad actor from abusing this to locate people. So yeah, I think we know what I'm kind of talking about. So one of the message types that are used in location services is called the area event request, and basically it's just a request to, it's just a message that allows you to request the position of a target mobile device, and it's triggered by a device entering or leaving a defined geographical area, and yeah, just basically what I was describing in the previous slide. And it's defined in this GSM spec here. So it contains several fields. There's the client ID field, and then there's the area definition field. This is what a very, very simplified version of the ASN1 definition of this message looks like. And it's complicated enough that it's worth trying to identify the code parsing this. So as you can see, like you have octet strings of defined sizes, so you can so the idea is that there's already constraints that the developers need to worry about, like size 2 to 7, size 10 of the area list, which is a sequence of other complex data structures. So yeah, I mean, anyway, so when when I found the area that was actually decoding this message type, I mean, the code certainly doesn't look like this, but I just kind of stripped it and simplified it. And yeah, so this is the simplest I could get it. I know it's a long function, but let's kind of read it together line by line. So there's this function that's called like ASN parse. It essentially just parses the ASN1 message without any kind of understanding of the data behind it. And you have the number of AEIs that it stores in an output parameter, which is like just a data structure, and it will store you. So you use in one. There's this thing called like a jump context, and essentially it's just the way the ASN1 parser bails out you. So when it's decoding a message and something fails, it would just do like a long jump back to a previous place to avoid. I mean, just to bail out of decoding. There's the number of AEIs, which is the number of total parsed elements. And here, when we look at the loop, it just kind of loops through this thing without any kind of checking on this AEI. So that's already something that looked interesting. If we can control this number of AEIs, we can kind of make an unbounded loop. And if we look at 3, we have like a memset of size 7, but there's just a for loop right after that, writing into the same buffer that's supposedly of size 7 without any kind of bounds checking. So basically, we have 2 bugs in this image. There's the first while loop, looping through an unbounded number of elements, and then we have the for loop, the inner for loop, which is writing data out of bounds in a 7 bytes buffer. So we have an OB and a buffer overflow, so we can attempt to exploit this. So in terms of exploitation, I guess the first thing I wanted to do was to find a way to debug the target. And on iOS, unfortunately, you don't really get any information except like a single line in the syslog that mentions the crashing address. And obviously, that's going to be really hard to work with. So after some research, I found that there's some older devices that are also running the Infineon baseband. You can find like older Asus phones, and they allow you to patch the modem and load it. There's no kind of checking, I mean, integrity checking or whatever. So the only problem is that the code differs quite a bit, but you know, it helps at least with reachability assessment. And what I mean by that is, you know, when you're reversing something like this, it's really helpful to get some information on data you can, and I mean, on code you can and can't reach. So just like the ability to set breakpoints essentially goes a long way in helping with reversing. So in terms of triggering this bug, the message that you need to send is facility is encoded inside a facility information element, and this can be found in a bunch of layer 3 messages, like a setup message, which is a message you use to initiate a phone call. There's alerting, which is also related to that, and then there's connect, disconnect calls, release, register from some different protocols and stuff like that. So unfortunately, the first thing regarding this bug is that there's a limitation, because in GSM, you can't send messages that are more than 252 bytes. And so essentially, we can't overflow as much as we want. And when you subtract like encoding bytes and stuff like that, you get even less data. So yeah, so the question was, my question was how to overcome this. And luckily we have, I mean, I wouldn't call it a bug, but there was some implementation inaccuracies. So the ASN1 definition describes the area identification, which was one of the fields of the message to be of size minimum 2. And the key here is that since we're trying to send many different elements in order to abuse this out of bounds, right? The fact that we can avoid sending even 2 bytes can save us a lot of bytes since we only have 252 bytes, right? So if you 250, I mean, just for example, 10 times 2 is already 20. So exactly. So the less bytes you could send, the easier it would be. Just as a result, then we could just target much further than just 252 bytes out of bounds. So the idea was to look for corruption candidates. This is essentially so remember when I was talking about the tasks and how they allocate a context object at the start? And this context object is essentially for the supplementary services task. You basically have like the parsed area event data, and a little below that you see this thing called I called it a QT. It's basically a pointer to some other tasks queue that this supplementary services task will use to send a message to that task. So when I saw that this was the layout of memory, I want to know what this send signal to queue thing actually does. Can we gain anything out of corrupting that dest q0 object? So luckily, it wasn't very relevant to look, because it just looked like this. So you have a magic at the head, at the start of this queue object, and then there's a function pointer that is called inside of it. Yeah, so there's no ASLR, and we control a pointer to this object. It's an easy win. Now what I want to say is, in terms of relevance of this, I discovered this bug in 2018 and it was patched in 2019. At least that was my thinking. The bug had most likely been there for many years, I think, and it turns out that until very recently it was only patched on x86 versions of the modem. Like, it was live and kicking on ARM versions, and we know that Apple acquired Intel. Like I said earlier, it acquired Intel, and could it be that they're trying to do something with this modem in the future? Yeah, so fortunately it seems like I missed the O-Day drop by 1 day. But yeah, this is from yesterday's update is when they fixed this bug. So before, I also want to talk about Shannon baseband a bit, because like I said, this talk is about attack surface selection. And around the same time where I was working on this project, I noticed that the ASN1 parser for Samsung had changed, and the code was clearly written by Samsung as opposed to being, third party or something, and it contained more bugs than lines of code. So that's just what I wanted to say about Samsung. Yeah, so the talk was a little short. I'm sure everybody was tired, so I didn't want to have people sleeping here. So my closing notes for this is, I don't know if this talk is relevant or not, but my guess is it might be soon. So yeah, that's it for me. And I want to say that we're hiring. We're a pretty cool company with cool guys working there, and we're looking for researchers basically doing any kind of hacking that's low level. And you can send an email here if you're interested. And yep, thank you for being here so late. So if you have questions, I think we have plenty of time. Yes.
So when I hear ASN1,
Yeah.
the bug that I've seen in, I think, all implementations of X509 that I've looked at is integer overflows, because you can encode arbitrarily large integers in ASN1, and then they get mapped to an int. Have you looked into that? Is that really a question?
So the question is that, I mean, they mentioned that the bugs that they've seen in ASN1 parsers is a lot of integer overflows because you can encode arbitrary length values in ASN1, and yeah, I do agree because of the way they encode integers. They can be encoded with 1 byte or 4 bytes, and I did look into that, and it seems that they were kind of handling this because of the fact that you can only send 252 bytes. There's kind of checks around for at least an initial check that it's not going to be, I mean, XFFFFF. So, yeah. Any other questions?
So now let's get you a mic. Last talk of the day, and now we have questions, guys.
Thanks. What's exactly the attack surface here? Like, what is the source of those ASN1 messages that are processed by the baseband? Is it do you have to have any special permissions on the device itself, or they come from the GSM network or whatever?
So yeah, they come from the GSM network. The attack surface is essentially, if you're able to get a device to connect to your GSM network, then you can attack them this way. Yeah. Does that answer your question? Yeah.
Any more questions? Please show of hands.
Here?
Yeah, wait, it's crazy. All day we haven't had questions, now we have them.
Think I know this guy?
So, yeah, I have a really simple question here. How long did you work on the subject before finding this vulnerability?
So this was in 2018. I don't remember exactly, but I think it was maybe 1 to 2 months. Yeah, prior to Pwn to Own. And I guess a funny story. I mean, I already told you, but I'll tell everybody is that I kind of found this bug right before traveling to Pwn to Own. And then I needed to kind of exploit it, and essentially my whole time in Tokyo, like 2 or 3 days before the contest, I didn't sleep, and it ended up exploiting it the morning of, but then I couldn't find anything meaningful to do with it, so it ended up being like a failed attempt, so I was pretty bummed. Yeah.
Hi, nice research. I was curious about the Q object. You mentioned that it has some magic at the beginning. Did you try to look for that magic? Like, is it some no implementation?
No, I didn't really look for that magic because the idea was that if you craft an object that just has that magic, then you'll pass the magic check and you can hit that function pointer. So
Yeah,
I didn't really.
I think it looks familiar. I think it's either thread X or nucleus.
So yeah, so this baseband is running thread X indeed.
Okay, thank you.
So, anyone else want to give you more exercise?
No.
Come on, I haven't have enough. Okay.
Good.
With that,
Thank you.
I think, okay.